Well, hey, in this video, I'd like to do a quick review of Unit 9 on earthquakes. Test 3 is going to be on Units 8, 9, and 10. So let's get right on a review of earthquakes. What I want to show you is kind of a listing of some of the topics in the first part of Unit 9. It focused on earthquake theory. So let's start off with the elastic rebound theory, which is our explanation for why or how earthquakes occur. Stress in the crust overcomes the strength of the rock, and the rocks break. While the rocks are under stress, they can deform, and they accumulate strain energy during that deformation phase. When they break, they release the energy, and the energy mostly comes out as seismic waves. We learned way back in the plate tectonics unit that most of our earthquakes occur along plate boundaries, but we learned in this unit there can be intra-plate earthquakes. A really good example of that is the earthquake sequence of 1811 to 1812 in New Madrid, Missouri region, known as the New Madrid seismic zone. There was a series of intra-plate earthquakes, and some of those were very, very large and damaging. I didn't have time this semester to go over induced earthquakes, but those are man-made earthquakes. Some human activities cause earthquakes. Usually those induced earthquakes are fairly small. Our best example today is earthquakes that are induced by activities associated with hydraulic fracturing of shale to get oil or gas, is also known as fracking. And a lot of the induced earthquakes have to do with the disposal of wastewater that comes up in the drilling process. Some earthquakes are also thought to be induced by the fracking itself, which is injecting highly pressurized fluids and sand into deep underground rock formations to break them up so that the oil will come out. Anyway, we did talk about seismic waves and how they can be used to determine the location of an earthquake's epicenter when a distant earthquake occurs. So let me quickly review that. I think I can go back to my PowerPoint. The two important seismic waves are the body waves, the P waves and the S waves. Remember, the P waves are the faster seismic wave and the S wave is slower. The farther the seismic waves travel through Earth's interior, the more that fast P wave gets out ahead of the slower S wave. So we can take a seismogram, we've put it vertically here on this graph, and those small P wave vibrations come in first. And at some time later, we get the first S wave, larger shaking of the seismograph. So the time lag between when that first P wave arrives and that first S wave arrives is actually related to how far away from the earthquake epicenter the seismograph station is. We can use a simpler graph knowing that then, and if we have the time lag on this y-axis here between the first P wave and the first S wave, we can use this line to determine the distance to the earthquake epicenter. Remember that you need 3 different seismograms that you analyze from 3 different locations in order to pinpoint the location of the earthquake epicenter. We can also use our seismograph records to estimate the magnitude of the earthquake. And I showed in the video the simple Richter magnitude. You need to know the height of the tallest S wave on the seismograph, as well as the distance that your seismograph location is from the earthquake epicenter, and those two parameters can be used to calculate the Richter magnitude. Remember, magnitude is trying to estimate how much energy was released during the earthquake, whereas intensity is estimating the damage done. So we can compare earthquakes based on how much energy they released, or we could compare them by the amount of damage they did. So another important aspect of what we try to get across in Unit 9 is the idea that the amount of damage done depends on a lot of different factors. We have some of those factors listed here. For example, obviously, a larger magnitude earthquake is likely to cause greater damage. But we have to think about the proximity to the epicenter location, because the locations closer to the earthquake epicenter would be expected to suffer more damage. That's because the seismic wave energy decreases with increasing distance away from the epicenter. Focal depth can matter because deeper earthquakes release seismic energy from way down deep in the Earth's interior, and those seismic waves lose some of their energy on the way up to the surface, so they don't have as much energy to shake things at the surface compared to a shallow focus earthquake. Subsurface materials, or the materials that underlie buildings, can be a very important factor that can influence the amount of damage done, because materials like unconsolidated, fine-grained mud amplify seismic shaking. Sand and gravel amplifies the shaking a little bit less, and the most stable material to build on is bedrock. It amplifies the seismic shaking the least. Building materials and the design of buildings is also important. For smaller structures, wood framing is a better option in earthquake-prone areas because the wood framing is flexible when it's shaken. For larger structures, reinforced concrete is a better option. And steel framing, where the joints have some flexibility, is another way to minimize the damage from earthquake shaking. The worst kind of building materials are earthen materials, things like brick, cinder blocks, unreinforced cement, just plain old cement, or adobe brick. In terms of design, the more interior walls there are in a building, the less the likelihood of upper floors collapsing or pancaking down onto lower floors. So open floor plans should be avoided, especially in larger buildings like mid-rise or high-rise buildings. Let's see what else we have. Can we predict earthquakes? No. Currently, we have no reliable earthquake prediction tool. Many different types of potential precursors to earthquakes have been examined to see if they could be a reliable warning sign that a big earthquake is going to happen. Those precursors include things like foreshocks, smaller earthquakes before the big one, changes in the concentrations of radon gas that we might detect in groundwater wells or coming out of the soil, changes in water levels in the groundwater wells, or changes in stream flow. They all sometimes change prior to an earthquake because right before the rocks break, smaller openings like fractures sometimes get a little bit larger, and that can influence the flow of fluids like gas or water in the subsurface. However, that has not been found to be reliable all the time. Same way with strange animal behavior, increase in the rate of slip along faults or creep, slow movement on hill slopes. All these different things have been examined, and none of them has proved to be a reliable indicator. So in the absence of a way to warn people that a big earthquake is coming, we have to make people more aware that the threat exists. And we do that by examining the historical earthquake activity in an area. We can examine the geology, look at faults, and try to assess how often those faults have moved in the past. And the seismic gap theory is useful in characterizing seismic risk. It's this idea, this fairly simple-minded idea, that when there hasn't been a big earthquake for a long, long time along a segment of a fault or an entire fault, that fault or segment of a fault is more likely to experience a big one compared to a fault that has recently had a big earthquake. Well, I tried to hit the highlights of some of the common things I ask about on Test 3 regarding earthquakes.